Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Alexander Rose, who's come to us from the Long Now Foundation up in San Francisco, where he is the executive director and the project director for the 10,000-year clock. He was the first employee in 1997 of the Long Now Foundation, and before that he has been an artist in residence at Silicon Graphics, and he was at the Art Center College of Design, and he got a Bachelor of Arts at Carnegie Mellon in Industrial Design. Alexander has worked on and started several projects with the Long Now Foundation, including the Rosetta Project and Long Bets Project, and they also have a very successful seminar series on long-term thinking. Alexander is also a robotic enthusiast. His projects have starred up at Burning Man, and he has participated in many BattleBots sequences and has also founded the robotic fighting league. So you'll have to probably check those out on YouTube and coming soon to a channel near you. But today, Alexander is going to talk to us about the 10,000-year clock project. So if you'll join me in welcoming Alexander.
Thank you all for coming out today at lunchtime. I'm going to start today with a story that I'm sure some of you have heard, possibly associated with this project. I think I spoke at SETI when I very first started, maybe back in 98 or 99. You guys were in a different location. And I see Doug here, who was one of our advisors on our Rosetta project. We've come a long way since then, both with the Rosetta project and with the clock project, and I'll be updating you on that process. This whole project really got started with this story, and is a story of these oak beams at New College, Oxford, which at least is partially true as near as we can tell, but the story holds either way. It was a story that Gregory Bateson told Stuart Brand, and Stuart Brand then told Danny Hillis. And when this hall was built in the 1300s, it was built with these giant oak beams that crossed the center section. And 500 years later, in the 1800s, when they had to replace these beams, they had become a bit rotted and the beetles had infested them, and they didn't know quite what to do at this point. You couldn't just buy trees like this or lumber like this in Europe anymore. And it wasn't until they spoke to the school forester who said, oh, well, we have the trees that you planted. And it turns out that at least the basic forestry practices of the times were that you would plant a grove of trees to replace the large oak beams that you needed 500 years or several hundred years later. And it was clearly this type of thinking that was not really going on nowadays. And Danny Hillis was a computer scientist, or is still a computer scientist and general kind of polymath inventor. I believe he was on your science board here at SETI. I don't know if he still is, I forget. But he had done some of the best work in parallel processing and developed machines like the connection machine with Richard Feynman to do massively parallel processing. And he had been working in this faster and faster space, and he kept realizing as he did that there was a slower and slower space that was being ignored. And that while there's a lot of things that need to happen very fast, there's actually a lot of problems in the world that can only be solved if you operate on a much slower time frame. Things like education, climate change, environmental issues, prison systems, hunger. None of these things can be solved in a next election horizon kind of time frame. And in fact, you have to attack them on a 50 to 100 or more year time frame in order to have any hope of solving them. And his idea was to do one project on a very long time scale. And his idea was to build this clock. And his original idea was a monument scale clock that would tick once a year, bong once a century, and the cuckoo would come out once a millennium. And this would be an icon to long-term thinking. And he told this idea to Stuart Brand, who had started the Whole Earth catalog and was very much a person who is interested in changing the way society thinks about various things. And Stuart thought, well, that's great if you get everyone's attention to think longer term, but then what do you do with it? And his idea was that there should be some kind of information service that goes along with this, that helps society and civilization understand itself on the same kind of time scale. And Brian Eno, who also became part of this conversation, who is a musician from the UK and an artist in general, also coined this term, the long now. When he first moved from England to New York, he realized that when people said now in New York, they meant a very different thing than what they said now in the UK, and that there was a short now version of that versus a long now version. We took that to and extrapolated it, and it was Peter Schwartz who was part of this email conversation and eventually became part of the founding board. He said, well, the real kind of human moment is the last 10,000 years. And this became the time frame that the clock was going to work in. This is when the last ice age really receded, agriculture began in different places around the world, and this is as far back as we can look in humanity and technology and civilization really beginning as we know it. So this is how far we should look forward as well. And so the idea was that we would build a 10,000-year all-mechanical clock. And just in contrast to the scale that I think SETI works at constantly, we are not working on a billion-year astronomic scale. We're not even working on a million-year geologic scale. It is this 10,000-year kind of Anthropocene moment, and this is about 400 generations at current generational rates. If you had to tell a story 400 times, that's kind of the problem that we have to solve on a societal level, and have that story be right at the end of or at least vaguely right at the end of the chain. So that's the kind of problem that we're trying to solve by going at this clock project and other projects around long-term thinking. I'll go over a few of the places that we started, and I continue to research in terms of precedents and lessons that we have from our own history. One of them is this object, the Antikythera Device, which is kind of a favorite of mine because it itself is a clock, and it is over 2,000 years old. It was found off of Antikythera, Greece, and once they pulled it up, they knew it was a clock, but they didn't know too much about it. They definitely knew it set back the known date of when things like differential gearing had been invented by quite a bit, by 500 to 1,000 years. And it wasn't until recent studies where they x-rayed the thing and were able to do complete reconstructions of it that they know that it was actually a full astronomical clock. There's no other example in the world, but it certainly shows from the expertise in its construction that it was not the only one in the world that had ever been built. But we have no other examples of it except for this one. And this is an interesting way of getting something to last for a long time. You can lose it. Now, of course, it has to be found, and it has to be found by the right people, and it has to be lost in the right kind of chemical environment and found again and contextualized. And in this case, it took 50 years or more. And the Rosetta Stone was kind of like this. It was found by one of Napoleon's soldiers, but he actually recognized that it was valuable, and it still took another half a century of decoding effort to understand what it was. There's other strategies for getting things to last a really long time. You can be really massive. And there's another interesting strategy that happened with the pyramids, and it's this kind of ablative armor technique, where the outer casing stones were taken from the pyramids in just the last maybe 5 centuries. The insides of them were looted probably within a century of them being put in there, but the basic pyramidness of them has remained. So one possible technique is this idea of putting valuable things into a space that people can take, but they don't actually take the true value away from it. And this is another example of that technique, where the Taj Mahal was encrusted with jewels all the way throughout. And it was looted several times, and finally by the English, who spent a long time prying the gems from the walls. And instead of destroying the whole building, as many other buildings were destroyed during that time, by the time they had finished pulling out, which are now the crown jewels, they decided to preserve the building. And it's unknown if they would have really decided to preserve the building if they hadn't been slowed down by those hyper-valuable items. So this is the kind of ablative way of armoring something to last through a long period. Now the other one is to take a really long time to build it. This is the cathedral at Cologne. This was started in 1248 and was sort of finished around 1880, but it's still under repair. You can see there's a scaffold on it right now, and it will be continually under repair. And there's other buildings that are doing this as we speak. There's Gaudi's Cathedral in Barcelona, and it's 100 and something years into construction, and probably is going to take another 100 to finish the design that Gaudi set forth. So this is an interesting way of solving a very real problem that I think we have with building a 10,000-year object, which is that there's the most dangerous time for something that you want to last for a very long time is the one generation after you finish it. And this is the time when it becomes unfashionable. And so, we saw this here in San Francisco when there were Victorians that were built, and they were all beautiful. And then the 50s and 60s came around, this modernist era, and everyone tore down tons of Victorians because they were old and unfashionable and put up tilt-up concrete things that I think may not hold up to the stand of time, as well as the Victorians. Maybe they will become the new valuable thing. Some it will, but I think to a large extent we regret the loss of a lot of those Victorian buildings that were taken down at that time. And that is the most dangerous time, and I think it's going to be the most dangerous time if we're going to build a clock that's going to last for 10,000 years, is 50 to 100 years from now, before it's become an antique and a valuable cultural artifact. And when it's just the first generation of people who built it are gone, there's that middle generation that is very difficult to pass through. There's other techniques for passing through this kind of chasm of obsolescence and unfashionability. There's the Eiffel Tower, and this was extremely unfashionable. It was built for a World's Fair. It was supposed to come down not long after. And the only thing that saved it, people thought it was a monstrosity. Every critic in Paris, you can imagine Parisians, any change at all, right? But the thing that saved this was that it was an unlikely radio antenna. And then it became a TV antenna, and then it became all these things. And so it was the best way to get reception in Paris of all these new technologies that happened to be coming out around the same time. So it was saved on a kind of yearly basis just for that reason. And so it was accidentally useful. And that's another way to have something last through that time of dangerous non-fashionability. There's also some unlikely materials that have come up and methods. And I think that when we all think about making a 10,000-year object, you immediately think of stone and ceramics and stainless steel and titanium as the only ways that you could possibly do this. However, we have in our own history things that are lasting very long time that have just been well cared for. And so you can actually design an institution that will last alongside of your object to maintain it. And this is a shot that I took. I'm about 8 stories up in a cathedral in Ely, England, and that beam is over 700 years old and is vaulting a huge cathedral ceiling, and has been basically unmaintained except for they maintain the roof. So, but this is in an awful preservation environment. It's in England. And yet wood has lasted over 700 years old. And if you actually look into the history, there's Japanese buildings that are over 1,600 years old with the same continuous wooden structure. And so, strangely, wood can be a millennial material if it's maintained properly. Now, another way of making a wood or ephemeral material building last is, again, keeping the institution going through a different maintenance process. In this case, this is Ise Shrine. And Ise Shrine is considered one of the most important temples in Japan, and it is rebuilt every 20 years in an exact replica of it. So this is a rare shot. This was taken almost 20 years ago now, because their new one is going to be finished in 2013. But the one down below is the new one, and the one above is just starting to be deconstructed. You can see the roof of one of the cross structures coming down. So every 20 years, they deconstruct and reconstruct, and a master teaches an apprentice. It's basically a once-a-generation reminder of why they're doing what they're doing. And you get, there's even arguments that this type of practice has allowed Shintoism to move along in parallel with Buddhism as it came across the Sea of Japan. And so this, everyone is Shinto, and some people are Buddhist and some people are other things, but this constant reminder has helped the institution itself last. And this process has been going on for at least a millennium, and there's arguments that it's been going on for over 2 millennia. Now, moving back over to this country and some more modern projects projects that have been intended to last for 10,000 years. This is Yucca Mountain Nuclear Waste Repository, now mothballed. But we went to go visit this when it was still under construction. And they have done a fantastic amount of really great science in how to make something last for 10,000 years. And of course, the first thing they realized is it has to be underground, it has to be in good rock. This is a map of what they're doing, and at the time they had only built those access ramps when we went to go visit it, but they're going to do this crisscross, or we're going to do this crisscross sections of underground storage facilities. And the great thing about this project, because there was actually there's a 10,000-year law on the books that the United States has to maintain this nuclear waste for 10,000 years, they had to do research that correlated with this. And very interestingly, some of that research crossed over our current clock site, in that they learned about different type of nickel alloys and materials that we're now using, and we get to use that research. But they also did research into concrete, a lot of research into concrete. There's a few places in the world where we have very old concrete, in some cases naturally occurring concrete. There's 2,000-year-old concrete in Rome, and that was created by the ash from the lime and ash from Mount Vesuvius. And other places in Jerusalem, and they looked all over the world for places where this same type of chemical compound of concrete was naturally mined. And one of the only places in the United States happened to be within view of our site in West Texas, which you'll see later on, which is a very strange coincidence that the only 10,000-year concrete known happened to be right near where we're building our clock. This is another site in nuclear waste site. This is a 100,000-year nuclear waste repository being built in Scandinavia, and outside of Finland, or outside of Helsinki in Finland. And I'm hoping that I'm going to go visit there actually very soon. I just got an invite to do that. And then the other way to build things to last for 10,000 years is not really don't build them to last for 10,000 years, but you build them for once in 10,000-year events. And so when the Dutch were faced with the same problem, actually a much rarer problem than the folks in the southeast seaboard were faced with, when basically doing nothing to prevent Katrina, the damage of Katrina, they spent $500 million building the Meslant Barrier, the largest man-made moving structure on the planet. And the design is for it to stop a once in 10,000-year event, which would be a hurricane, effectively, in the North Atlantic. And they've already closed it many times and saved minor flooding just in the time that it's been built. And so we'll see if the folks of the southeast start taking this type of thing more seriously. And I think in the United States we tend to think more about insurance and less about prevention, but we'll see. A place that I'll show a few more slides of, just because I was just there. I just traveled to Svalbard to the International Seed Vault. Now this is designed as a 1,000-year facility. The idea is to provide a backup to all the world's seed vaults. And so if all the national seed vaults send copies of all the seeds that they have there, and they put it into the permafrost, where it can, just the permafrost temperature alone there will keep the seeds at a viable temperature for at least decades, and then they chill it down even further so it can last, some seeds can last hundreds and if not 1,000 years. This is what it looks like as you fly into Svalbard. That's the airport there on the left. And this is what the underground facility was designed as. They built this extremely fast. It was conceived in 2005 and finished by 2008, and I was really shocked to find that out. And so when I got a chance to go in, they only open it 2 times a year, and they didn't really design it for visitors. I wanted to go see how they built it. Now, one of the first things that I found when I got there is they've already done retrofits, and that's already flooding. That the way they designed it so it slopes downhill, the frost builds up on the walls, and then when it melts it runs down, and so they've already had to put in pumps and things like this. And this is a recurring theme that I found in a lot of underground facilities that have been designed for a long time, is they always assume that they can keep the water out, and they're always wrong. You have to assume the water will get in, and you have to plan for that and route the water, not try and stop the water. But the most interesting thing about visiting this site to me was this book. I signed into this visitor book, and as I flipped through it, there was Jimmy Carter, Ban Ki-moon, whole delegations of Congress. And I was in the northernmost permanently inhabited place on the planet, and yet all these people were coming. And the one thing I realized that you build a really weird thing in a really weird place, and people will come and visit it. Don't think that they won't. And make sure you design it for visiting, because this place was not. They don't want to open the vault doors because it messes with their cooling system and all of that. And this is what the underground vault hallway looks like. That one door in the middle that's covered in frost, and you can see the chilling pipes going into it. Chilling it down to -18°C from the ambient -5°C, and that's what that door looks like. And then inside are all the seeds. All the seeds are put into these very normalized boxes, these plastic boxes, except for the USDA, which will only send them cardboard there on the left for some reason. Another 1,000-year facility that I visited, this took about 9 years of asking to get an invitation to this one, and this was the last picture they let me take before they took my camera away. This is the Genealogical Vault that the Mormons have in outside of Salt Lake City on your way up to one of the ski resorts there. In it's up Alta and Sober up that way, and it's in Little Cottonwood Canyon. And it's in great granite rock. They had it built by a guy who was their architect who had built all their schools at the time. They built it in the 60s as a kind of a reaction to the Cold War, worrying that Salt Lake City and their Mormon archives were, of course, going to be a major target of the Russians. And so they built this vault as a kind of nuclear hardened vault for all their microfiche of genealogical information that they didn't want to lose. And it's a pretty interestingly designed facility, and they also had this problem of flooding. It's only about 40 or 50 years old, and it's already flooded 3 times. They don't keep any of the lower drawers filled with any microfiche at all because of the flooding. They've had to cut trenches in, and these trenches now go right under these nuclear hardened doors, vault doors, to allow the water out so that they don't flood. So they're obviously a lot more worried about water than they are about the nuclear threat at this point. And the last example that I'll show is this one. This is kind of the counterexample, and probably the largest challenge that a project like ours has to face. These are the Buddhas of Bamiyan, or at least one of them is a before and after picture. The picture on the left was taken in 1963. The picture on the right was taken in 2003 after the Taliban spent many weeks destroying it. And as symbols of religion go, a Buddha is a pretty innocuous one, but it was still enough of a symbol of religion that the Taliban didn't want to espouse, that they spent money and time destroying it on purpose. So this danger of getting involved in the wrong ideology is a huge one, and it's hard you never know what your ideology of an organization you were part of may become over this kind of time frame. So there's several conclusions that we've drawn from looking at all these historic examples. One is that you should make it fairly remote. Cities churn a lot faster than rural areas. But the people will still come if you're trying to make something that you want people to visit. In our case, we are. We also want to make it remote for another reason, which is that part of it is when you make that journey to go there, you're having a conversation with the people that you're going there with. You're making this commitment to go. And I think that that conversation is very important. Water will get in, and so you have to divert it instead of trying to stop it. The oxidization control is an interesting problem, and I'll talk a little bit about how we solve that, some of the materials choices that we used. But some of the very delicate parts we're going to have to encase. Design it to be both lost and found. So to be able to, if this clock is keeping time, it may be lost for some amount of time, and then it may be found. And how do you address that problem? How do you want people to find it if it hasn't been maintained for 100 years? What are the fallback scenarios in the way it's designed and maintained? Make it difficult to disassemble. Basically, we're building a ship in a bottle. We're building a space that has very narrow ends and really big parts in the middle. That helps to reduce the enticement of using the site as a mine for the metals that we've put into the mountain. The other one is you design a long-term institution. And so far, no one's designed a 10,000-year institution. There's a few multi-millennial traditions, religions, martial arts, woodland practices, viticulture, stories that have lasted 3,000, 4,000, 5,000 years. So we're in that zone, but still no one knows how to solve the problem that we would have to in order to actually maintain and contextualize this forever. And the last one is the one I don't really know what to do with and how we would do it, but we could do something like this ablative layer, something where we actually put some valuables to be stolen so that people think that they have walked away with the most valuable part of our installation and not without destroying it. And so as we started to design this clock, we set forth a set of design principles that Danny Hillis worked on very hard, which was these 5 here: longevity, maintainability, transparency, evolvability, and scalability. Most of those are fairly self-explanatory, but the idea is that people will be able to maintain it, they'll be able to evolve it, they'll be able to, if we show a certain calendar system, for instance, maybe there's no calendar system that has lasted for 10,000 years, so we want to be sure that can be changed over time. That can represent an ideology that will certainly have to evolve along with it. And the scalability allows us to build small prototypes and work our way up towards large ones. The first prototype that we finished in 1999 had this dial on it. This prototype is now at the Science Museum in London at the end of their Making of the Modern World exhibit. And I'll just show kind of one of the types of problems that we solved as we worked on this. And the clock we designed to synchronize itself to the sun on any sunny day. And I'm sure many of the planetary scientists in the room would know what this strange figure 8 is. This is the analemma. This is a picture of the sun taken at noon every day through the course, not every day in this case, but maybe every week or so through the course of a year, and it creates this figure 8 shape. And this is representing what is called the equation of time, right? So there's a difference of solar noon that's about plus or minus 15 minutes through the course of the year. Now, the funny thing about that equation is that if you want to predict that equation at a 10,000-year time frame, you also have to account for the fact that the Earth is precessing on its pole every 26,000 years with the equinoxes. You also have to account for the fact that it's slowing its rotational rate by a second, a century or two. And so it turns out that there's also a whole other element here, which is climate change as well, which is the uncertainty factor of this equation. But the most certain part of this equation was filtered down into this 3-dimensional cam, which is effectively a disposable item for every 10,000 years the clock operates. This is the equation of time as it evolves over 10,000 years, and that follower that's kind of coming in from the back there would go up it once in that 10,000 years. Now the part of the clock that focuses on the sun actually has to kind of servo in on the sun using thermomechanical properties because of climate change. And it turns out that as the poles melt, the water can sling out to the outside, slowing down the Earth, and if the poles freeze, that's going to change the rotational rate. And JPL did the calculations for us and said that effectively the worst case scenario is about 23 days off of where you think the sun would be, plus or minus. So we have a fairly large window that we have to capture looking for the sun in the sky. And of course, if you're making a 10,000-year clock, one of the first things we discovered about doing calendrics is that we have to add an extra 0 to the date, solving the decamillennium bug a little ahead of some other people. So this was the very first prototype. As I said, it was finished in 1999. It also used the lower part of it there that you see also uses a different type of calculation system that any clock had used up to that point. It's a binary mechanical system. So the idea that you use analog gears to do all your math, when you're starting to calculate with really large numbers, the number of times some of those gears would have to go around and rub material off of themselves, and then the next time they come around, you have this additive error that starts building up in your system. To have something that's going to be accurate enough for 10,000 years is difficult. So you use binary mechanics, which is just a lever that's in a 1 or 0 position, and you do addition with that. And so each one of the plates below is a dial.
The scale?
The scale of that is about 8.5 feet tall. This was a small prototype. And since that time, we've been scaling up and or doing designs of things that we hadn't done in that one as we scale up towards the monument scale version. This is another type of display that uses that same binary mechanical addition at the bottom. Those bottom plates there. But it's calculating the human eye visible planets. So this keeps up to date the first 6 planets, basically. And this artifact is also about 8.5 feet tall. This is in our offices in Fort Mason. You can come by and take a look at it any time. It's kept up to date. And now we're scaling up to full scale, to the monument scale. And this particular prototype was the first prototype of a system of ringing a series of 10 bells in a different sequence each day for 10,000 years. So another type of mechanical computer. This one can generate over 3.5 million combinations of bell ringing sequences that were worked out by Brian Eno and an ambient music guy. And so this one has about 12-inch diameter, what are called Geneva wheels that do that calculation. And this is just last week, we got one of the first ones back. This is all done in 316 stainless steel. This can actually last for 10,000 years. It's sitting on a ceramic bearing that we made in-house. And this is the first of what will be 20 of these Genevas stacked in a big vertical underground space, which I'll be showing you. And as I said, we're using ceramic bearings throughout. And some of you who have worked in satellite and aerospace industry know that the ceramic bearings were invented really for satellites to operate without lubrication, but for the most part they were designed to be used in very, very light duty, where they may open up a solar panel once in their whole operational life, and or maybe go back and forth a few times with some jets or something like that. But we needed them to operate on about 3.5 million to 6 million cycles with no lubrication. We decided that lubrication always attracts too much dirt and always can flow out of the bearing, so it's too difficult to keep something lubricated. The other advantage of using ceramic bearings is that they can't micro-weld like steel bearings do, or stainless steel bearings. Stainless steel bearings, if they have a lot of weight on them, they just sit there and the micro vibrations will eventually weld them together. The other thing that it stops is this problem of corrosion that I talked about earlier, which is called galvanic corrosion. And so when you have two dissimilar metals, which generally the shaft and the outside material, we're using like A286 stainless steel and 316 stainless steel, that slight difference in chemistry on the galvanic scale will eventually cause corrosion between the elements that you really want to be moving, not frozen together. So the ceramic bearings give you an isolator for that, which is great. The other type of bearing that we're using for some of the very, very slowest moving parts, this is a small prototype. This is only about a 4-foot diameter, but there's one wheel on the clock that will have show all 10,000 years in it, and it only moves millimeters per year, basically. It's 15 feet in diameter. It's made of stone. And how do you make something that moves so slowly and is so massive? How do you allow it to turn? And this bearing was built, it's a walking bearing basically, and each one of those little wheels that were at the bottom that you saw flipping back and forth are actually flexures. So there's no rolling friction in this at all. It's just metal bending back and forth, and it's passing one from one bearing to the next one on that outer wheel. And that outer wheel only turns once in its entire design life, so it's not going to wear out. And the flexures are kept well within their flexing modulus, so they don't wear out. So a rolling bearing with no rolling elements. What we're working on now is the main power system, and I apologize that I'm not going to show you the entire design of the clock in the underground facility. We're actually we're not sure if we're going to show that. We kind of want people to come see it, and to show the weird kind of view of an underground facility that no one ever gets to see, as opposed to the way we've designed it to be experienced, seems a little odd to us. So I'm showing you little kind of pinholes into this process, What you see here is the design of the whole power system, and that's a big, huge weight that's at the bottom of it. And these really large gears here, that works? These really large gears here. So the scale of this is being held in a 12'7" diameter vertical shaft that's going to be cut into the rock with a thing called a raise bore. Same kind of drill that was used to rescue the Chilean miners. In fact, the drill we have is one of the ones that was there in Chile. So this is about an 8-foot gear. And not only is that an 8-foot gear, but that gear is a special gear. It's a cycloidal bevel gear where every single one of the teeth is cut in a 3-dimensional way, so that as the ceramic rollers that come in contact with it touch it, they actually don't, they never have scrubbing type of friction. It's always roller friction. And most gears are kind of idealized this way, but very rarely are they cut in that fully 3-dimensional way for every single gear tooth, especially at this scale. So this is a 316 stainless steel gear with all 3-dimensional gear teeth. Now we're working at the site. We have full-time staff at the site. This is an aerial shot that was shot by a friend of ours from a plane just recently. It's kind of low res with his BlackBerry, I think. But as I said, the tool that we're using for doing the main excavation is this tool called a raise bore. And if you follow the rescue of the Chilean miners, they used one of these to do the downward drilling. They can only drill that about 25 inches in diameter maximum. In our case, they'll be doing it about 20 inches in diameter, and that was what they had to get those guys up in that capsule. But normally the way these tools are used is they drill that pilot hole down, and they drill it down to a tunnel that's been excavated, and they hook up a really large bit, and they pull that up through to the top. And that's what the tunnel is we're doing down below, is to meet that. And then this raise bore will come in, and it will pull our 12'7" main excavation. And from there, we actually have a pretty complex underground construction that actually can't be done with drill and blasting. We want to build a spiral staircase that allows people to walk up and around all the clock works. The idea is that it's kind of architectural in scale, and that people can walk through the workings of the clock itself, and that we may even flare the tunnel out to kind of force perspective. As you can see, this is kind of a conical shape on the outside there. So there's not really very many methods that allow you to do that, and we had to start combining technology from both the mining industry as well as the stone cutting and quarrying industries. This is an underground marble mine in Carrara, Italy, that's cut with these diamond-toothed chainsaws that are normally run with just hydraulics and don't have any computer controls to them. So we took one of those blades and put it and built an 8-ton robot that can manipulate it in 3-dimensional space. And this is a test that was just done literally last week, where we tested it. This is going through 5 feet of concrete that was specially formulated to be the same density and chemical mixture of our stone. And so that's a 9-foot blade that's impregnated with diamonds that come off at a certain rate just for this material. And we'll be able to do a lot of our underground construction using basically CNC process, where you do a cut and then you break away in between the cut, and then you're left with a nice, at least a reasonably smooth shape afterwards. You can cut everything, but I think there's an interesting pattern to this smooth, rough that we'll be able to get out of this. That was an hour, that time lapse. So in order to cut the whole staircase, we have about 250 feet of staircase to cut. and it's 3 cuts per stair. And it looks like it's going to take us about a year of solid cutting to cut that staircase. And that guy has to sit there for the whole thing. So that's the clock. That's basically the current state of the clock project. We are now building these full-scale parts of the clock. They're all coming. They're being built in shops in Seattle, LA, and the Bay Area. They're all coming together in our assembly facility in San Rafael, not far from here, where we assemble sub-assemblies, take them back apart as little as possible, put them into shipping containers. They go out to Texas, and they're going to go into the underground facility once that's all done and sealed up. And the first question is going to be, when are you going to be done? We don't have a schedule for when we're going to be done. We don't have a budget for how much it's going to cost. We do it on a quarterly basis. We review it with Jeff, and we just do it as fast as appropriate and as efficiently as appropriate. The other side of this project is an information-based project, and I wanted to touch on the Rosetta project because I'm here and I think it has a lot of relevance to SETI, and it was how we contacted Doug Vacoccia, and talking across huge chasms of space obviously is very much like talking across huge chasms of time. And we realized that if we're going to help civilization through any chasms of time, or understand what is now a increasingly smaller and smaller set of languages in the world, and the data that comes from the past into the future from those smaller subset of languages, they need what is basically a modern Rosetta Stone to avoid this problem. This is the Festos disk. This is still well, there's some people who claim to have decoded it, but there's no widely accepted version of what this says. And it's also a good example of why pictograms, which are often thought of as the way to communicate without cultural bias, it's actually the worst way, because each one of these pictograms, let's say, this little ghost figure here. I mean, is that a little ghost figure, or does that mean somebody from the afterlife? Does that mean there's some guys, some priests who wore sheets? Does that mean that's the Masons at the time wore sheets? We don't know. But actually, phonetic alphabets are vastly easier to decode, it was the hieroglyphics on the Rosetta Stone that were the hardest thing to decode, and it took the other 2 scripts to decode that after 50 years. And so we started collecting languages, just little sketches of languages, basically 10 different elements, including a translation of Genesis, because it was the only thing that has translations on this, anywhere near this number, and where the language is spoken, the phonetics of the alphabet, and things like that. And we were able to micro-etch them onto a disk about 2.8 inches in diameter that has 13,500 pages on it. It was written with a gallium ion beam into silicon and then plated onto nickel so that it could last on the same timescale. One of these disks, the earlier prototypes, was launched on the European Space Agency's Rosetta mission, which I think gets to the comet that it's heading towards in 2014, November, I think. But it'll be kind of one of the only pieces of human content on there. But you don't need to build a DVD player, for instance, to read this thing. It's just pure optics. You can just zoom down into it with optics, and you saw that one design of the human eye readable side allows you to see that, and it spirals down smaller and smaller, so it would kind of hopefully encourage tighter and tighter inspection. Adrian mentioned we have a speaking series, and one of the very first speakers in that speaking series was Jill, and I was looking at her talk as I prepared for this one, and so I stole a couple of her slides from almost, I think, 10 years ago almost, and this was one of them, and I thought it was an interesting one where obviously SETI and the Long Now Foundation cross over. If there's technological disaster, if society doesn't have continuity, then the idea of SETI doesn't work. We need civilizations to have a higher level of technology, and most likely for you guys to detect them, at least from what I understand of the process. So if our level of technology doesn't keep increasing, then there is no way to detect each other. And the this idea that SETI is the archaeology of the future, as Phil Morrison said, I think is a really important idea, and I think it's one that resonates well with a 10,000-year project. And I was reminded of that when I saw this picture. Now, I've seen this picture referred to as both a positive story and a negative story, and it's hard to know which one it is, but once again, it was a once in 10,000-year event story. And this was a monument that was put up in Japan, and on it it said, "High dwellings are the peace and harmony of our descendants. Remember the calamity of the great tsunamis. Do not build any homes below this point." And I've now seen this referred to as homes were built below this point, and I've seen it referred to as no homes were built below this point. So I have yet to truth this out, but I think it's an interesting one, and if another civilization were to find our planet and just find that warning, or if one of the things we receive as a signal from another place is a warning, how well will we heed it, is a really interesting question to me. Thank you very much.
The power source is just a heavy stone that's going to take 10,000 years to drop?
No, it can store as it's currently calculated about a century's worth of power. That power is all the chime mechanism. That's kind of the most power hungry part of the clock. The dials themselves are actually powered by the visitors when they wind it, and that stone is also powered by the visitors. But the clock keeps time by a temperature difference from day to night that's collected up at the top of the mountain. And so only the escapement and the pendulum are kept powered by this temperature difference. So we conserve a lot of power. And then when people arrive, they wind it to make all the dials and the chimes go. And the clock, when it just stops at the right moment. When it always knows when now is, but you have to wind it in order for it to show you. And this is also part of that, design it to be lost. And the interesting piece of information you get from this process is when the last person was there. So when you arrive, the date and the time that's shown is the time of the last visitors. It could have been yesterday, it could have been 1,000 years ago. And so now, and if it was 1,000 years ago, you have a lot of winding to do. And if it was yesterday, you have a very small amount of winding to do. So the idea is to both encourage that interaction, which we realized with our first prototype in London behind a glass case, that not having that interaction is a bad thing. People want to kind of leave their mark and have their moment with it. And it also gets us out of the engineering problem of engineering a power source for all these really power-hungry parts of display and chimes.
Alexander, you mentioned the water problem, but you didn't mention your solution. Is that because that's still in the future? Or?
No. It's in our underground design. Basically, all of our underground spaces drain outward. And so, and even the way that saw is designed to cut those stairs, it has a droop angle in the blade, which we left in instead of trying to compensate for it. So it keeps a kind of an angle that even water that gets into the main vertical shaft, it will come to the outside of the stairs and spiral out and then come out the lower tunnel. The entrance tunnel to the top drains out through all of that. So the idea is that we know we're going to get water in, and we just keep it to the outsides of the walls away from the machine and let it drain out.
I have a kind of a silly question. You mentioned that it's next to the space thing that he's interested in building. What kind of protection do you have of stuff falling on top of your clock?
The only exposed part is the part that collects sunlight for the solar noon trigger and the power. So it would really suck if that got hit. We don't have protection from that. We haven't finalized the design of what that little cupola might look like. I think it's going to be a trade-off of how attention-grabbing we want it to be or how natural we want it to look. But at least from my understanding of the Monte Carlo predictions of launches, it doesn't sound like there's going to be enough to warrant any serious engineering around that problem.
Yeah. What type of escapement do you use, and will it tick?
So this was an interesting problem, is that we had designed that final dial chamber where the main dials and the escapement and the pendulum are, is this egg-shaped, and we had designed it so that we put it in exactly this kind of nodal point so that it would echo a tick to where you stand to update all the dials. And then as we refined the escapement design, which is actually a novel one that we've patented, we realized it doesn't tick. And ticking destroys clocks effectively. So ticking is the thing that hammers down on that's what you're hearing, is this hammer action on the escapement, which is the fastest moving part in our whole clock, which moves once every 10 seconds, which is several billion cycles in our, probably 15 billion cycles in our time frame. Now, that's not out of the realm of materials. 15 billion cycles, I think 5 billion cycles is about how many times a Rolex ticks in 20 years. So this would be, it's certainly in the right realm, and you keep it very soft. But we've engineered a lot of the tick away. So there's another part of the escapement, a wheel, that we've kind of made a resonant drum on that will hit something that actually ticks on purpose. So we had to engineer the tick in. But if you're more interested in the escapement design, I can show it to you in more detail. It's we're just now getting the latest version of the escapement up and running. Oh, sorry. We have a mic.
So if you're building it to be lost for a long time, and you're worried about flooding and oxidation, have you considered building it somewhere with little or no atmosphere, and not necessarily on this planet?
Right. The point of this project is to capture the human imagination. And I think whether or not people go and visit it, I think they need to know that they can go visit it. And there may be a time when extraplanetary visiting is much more possible than it is now. But the idea is, well, it changes your budget by about 3 zeros, right? And and you need a launch vehicle and all those things. So there's certainly been talk about it, and we certainly like the idea of launching certain parts of the information around the clock, like the Rosetta disk, and welcome more opportunities to get on launch vehicles for the parts that I think we could do that with, that are light and easy to get into orbit at this point.
Yeah, what's the composition of the rock and where you're putting this, and also what's the seismic history there?
It's Dolomite Limestone, and depending on where in this range, it can be pretty brucitic. We're a little bit a ways from that, where this marble mine is, where they actually mine the 10,000-year concrete. That was superheated from a very old volcanic eruption. The seismic history is they have had earthquakes even in recent memory, but it's way better than the West, this part of the West, by a long shot. There's certainly, places like Australia would probably be even better. People have suggested places like Ayers Rock. They basically have no earthquakes, but this site came with a funder and a reason to do it, and I think things like that cave certainly show that things can hold up on this time scale if we build it right.
So the North Pole, our North Pole, is pointing to Polaris now, and will 10,000 years from now point to Vega and Lyra, I think, and that is
close to
built
Vega,
in the cam that you showed, multidimensional cam.
Yeah. So actually, in that star field that you saw, that whole star field is a hemisphere that's slightly off axis. That is rotating, and will bring Vega around in about 13,000 years, I think, when it becomes the North Star.
How confident are you in the current corrosion data on oxidation, humidity, and how confident that you can extrapolate that for 10,000 years?
Well, even though we're using modern.
It's not impervious.
No, it's not. No, stainless is not impervious. Basically, I think that the best comment I got from our kind of material science guru is everything is burning. And in our atmosphere, everything is effectively burning in oxygen. And so the question is what rate? Now, as I pointed out, some woods have lasted on a millennial scale. They found a 5,000-year-old leather shoe in Armenia recently that was buried underground, didn't have much oxygen to it. We're using a lot of the data that was developed for the Yucca Mountain Nuclear Waste Repository. The other thing that we've done is that basically the operational parts of the clock are, and the stainless parts have huge tolerances. Now we're building them with modern machining technology that has 5/1000ths of an inch tolerance, but the operational tolerances of those parts is actually like a 1/2 inch, like for the chime mechanism to work and things like that. Parts of the escapement, which have to be much more tightly held, are using sapphire, ceramic, and in some of the large wheels that have a lot of teeth, in titanium that can have kind of soft pallets, so they just don't hurt each other. But nobody really knows. We know, we certainly know that things like ceramics have lasted 10,000, 20,000 years. We have examples of them. Metals, we have much sketchier data. I mean, the metals have lasted in natural environments on millions of years, but how much oxidation they got, we don't know. But we're operating on the best data that we have.
It would seem like another strategy for lasting 10,000 years would be duplication. Are you planning your second one?
Yeah, well, there's many ideas, and we post all the other people's ideas for a 10,000-year clock. I mean, there's only one way to make a 10,000-year clock, a big, ridiculous mechanical object. I mean, you could plant a forest of bristlecone pines. You could make an erosion-based thing in a river. You can, there's all kinds of great ideas that you could do for a 10,000-year clock. And we have built these other prototypes, which in effect are kind of 10,000-year clocks in and of themselves. We've had invites from various places in the world to build a city version of the clock, and we may follow up on those. We also have a whole other site in eastern Nevada, which we originally purchased to build the monument scale clock, that is covered in bristlecone pines, and is also a limestone site that we can use. It's much more seismically active. But we'll see. It's obviously a funding issue and how much attention we have to keep going on different projects at the same time. But we have certainly considered multiple clocks. And we'd love to do a little one for people to have in their houses too. So.
For those people who, I know there are a number of questions still remaining, I encourage you to come up and talk to Alexander and after the talk. Alexander, you mentioned that the Taj Mahal was covered in encrusted jewels to discourage people from wrecking the building. Maybe this artifact might be something that people would be interested in 10,000 years hence. We offer you a SETI mug.
Thank you.